Right, we're on to chapter 10. So we're going to go ahead and just get started with that. And again, let's see. All right, so last time we were talking about, we did the t-statistic for one sample t-test, and now we're going to look at how that might be done for two independent samples. All right. And for this chapter, you should have it under control about what sample variance is, as well as the standard error formulas. And the t-statistic from last time, as we're going to add to that, as well as what distribution of t-values are, the degrees of freedom for the t-statistic, and estimated standard error. All right. All right, so the independent measures design. So before we were looking at calculating the t-statistic if we collected one sample from a population of interest to see if there was a difference between a treated sample and the population. Now, and this is usually how most studies are designed, in fact, we usually will collect two samples from the population of interest. And so we would collect data from two completely different independent participant groups or for them. And these are known as independent measures or between subjects designs. So if I collect samples from two groups, I usually have a control group and an experimental group. And one of the groups will experience the my treatment, whatever I want to test them on, and the other group typically does not. And then we're able to make comparisons between the two. Or these t-statistics can also be used to test data from one group at two different points in time. So you select a sample and you may test them before they experience your treatment, expose them to your treatment, and then test them again after the treatment. Or if you have two different kinds of treatment, you might use the same group in both the two different kinds of treatments to make comparisons. And we call this kind of t-test a repeated measures or within subjects research design. All right, so there's a between subjects or independent measures research design, and there's a repeated measures or within subjects design. Using those terms for each of those types of research are used interchangeably, and so you should sort of get it straight in your mind. Which one has two separate independent groups, and one in which it is used the very same group, but in two different conditions. So. All right. All right. So the way you compute the between subjects and within subjects designs for the t-statistic are very different. So each design has different strengths and different weaknesses depending on which one you're doing. Only the between subjects design are we're going to only cover the between subjects design in this chapter, and we'll go over how you do the repeated measures design in the next chapter. Okay. All right. So for the independent measures t-statistic, the way we would think of the null hypothesis is that there is no difference between the population means. So HO is the mean from the first group minus the mean from the second group. And here, since all of this is hypothetical, right, we're saying that the population in one condition from would be completely different or not different, I should say, at all from the population in another condition, right? The alternative hypothesis for the independent measures t-test says that there is a mean difference. It does not equals 0. So the null hypothesis for an independent measures t statistic says that the difference between your groups is 0. The alternative hypothesis says that the difference between your groups is not 0. There's a difference. All right, so the formulas for the independent measures hypothesis test are as such. So the equation for a one sample test was the mean from your sample minus the mean from the population divided by the standard estimated standard error. And for the null hypothesis, that would equal 0. So the basic structure of the two-sample t-statistic looks like such. The mean from your sample minus the mean from one group and the mean from the sample from your second group subtracted from the hypothetical population mean from one group and the hypothetical population from the mean of the second group. So since the null hypothesis says there's no difference between the population means, so therefore the means subtracted from one another equals 0. So this sort of cancels itself out. So when you are calculating the t-statistic, you should understand that this is really what's going on. You are finding the difference between your sample means and your two population means, and then dividing by standard error. However, since this equals 0, the null hypothesis says that there's no difference, we can sort of drop that from the formula and just look at the formula simply as this. All right, so it's the difference between your two sample means divided by standard error. So you have to, however, we have to calculate standard error from both groups. Okay, and we'll look a little more into that. All right, so to determine how much difference is reasonable to expect between your two sample means, if the null hypothesis is true, we have to calculate the average distance of the two samples and the population parameter, which remember equals to 0, so we dropped it. And we do this by adding the standard error between the two samples and then dividing. So here in a one sample t-test, the estimated standard error formula looked like this. Now our estimated standard error for a two sample t-test look like this. All right. So it's essentially for the first one, for the one sample t-test, we're just finding the square root of standard error divided by n. Here we have to do that for both groups, add them together, and then find the square root. All right. All right, so variability of the difference scores. So the variability for the difference in scores is found by adding the variability for each of the two populations that you have, right? So why should you add sample measurement errors, which are squared deviations from the mean, but subtract sample means to calculate a different score? Good question. So why do we subtract the means between the populations, but when we're calculating for standard error, why are they getting added together, right? So look carefully. Here, we're adding instead of subtracting. All right, well, let's look. We add measurement errors to get the total variability, right? So we want the total variability in both of the samples. And then we also need to subtract the means from both of the samples to find the difference between the samples, all right? So here we have two population distributions in this picture here. The score in population 1 range from 50 to 70 points, which is a 20-point spread. So see from here, between this sample distribution to the second sample distribution, the smallest difference here is 20 points. And the scores in the population 2 range from 20 to 30 points, which is a 10 difference spread. If you select one score from each of these two populations, the closest two values are 50, or x equals 50, and x equals 30 from the other sample. And the farthest away are x equals 70 and x equals 20. So because each sample's variability differs, we add the whole variability. And not only can you see the difference by making comparisons from the numbers, you can even see the shape of both of those samples is different. The sample from population 1 is more spread out than the sample from population 2. All right. So we need to add up the total variability from both samples. All right, so here this shows the standard error calculation, but it's unbiased only if the two samples are exactly the same size. So that means you've collected a sample for group 1 and another sample from group 2, and both ends for each sample have to be the same in order for it to be unbiased. But that's sort of difficult to do, right? A lot of times in research, if you actually were to do this on a pretty regular basis like I do, you'll find that you will often end up with different numbers in both of your samples. You know, I might get fewer people in one group than the other for different reasons. So when the two sample sizes are different, the standard error formula is biased. So we have to use pooled variance, and it provides an unbiased basis for calculating the standard error. And so you can see here, we would use degrees of freedom. All right, so first we use pooled variance, and we calculate that using this formula, sum of squares from each group, the degrees of freedom from each group. And we add the sum of squares and then divide by the sum of the degrees of freedom from both groups. And we place that in the numerator and divide by the total n from each group. All right, so pooled variance and degrees of freedom. The degrees of freedom for the t-statistic is the degrees of freedom for the first sample and the degrees of freedom for the second sample. So those will be two different numbers. For the independent measures t-statistic, the sample mean difference minus population mean difference, which is zeroed out, is divided by the estimated standard error. All right, so you can see how that is calculated there. First, you need to calculate for pooled variance. And we just sort of went over that. All right, so we need to calculate for this, and the first step would be to calculate for this. All right, so let's see what that looks like. It might be a little difficult to understand if I'm just sort of pointing and clicking right here. So let's look at an actual case and how the numbers will work out. Here we have a statistics teacher who wants to compare his two classes to see if they performed any differently on the tests that he gave them that semester. Class A had 25 students with an average score of 70 and a standard deviation of 15. Class B had 20 students, so a different number of students, with an average score of 74, a standard deviation of 25. All right, so using an alpha of 0.05, how did these two classes perform, or did these two classes perform differently on those tests? It's pretty close, right? So although visually one did score higher, 74, than the other, but this one had a spread of scores that was a little higher than the other group. So how does that actually turn out to be? Is it significantly different, or maybe it's not? All right, so first you state the hypothesis. Remember the same 4 steps. State the hypothesis, select your alpha level, locate the critical region, and we use the same t-distribution table. Obtain the data and then compute the t-statistic. Then you make the decision, all right? So same example here. So we're going to state the hypothesis and select the alpha level. So to do so, you would state what the null hypothesis is and the alternative hypothesis. The null hypothesis states that class A is the same as class B. The alternative hypothesis is that class A is not the same as class B, and our alpha level is 0.05. All right, that's step one. Step two, okay, where's the critical region? Ooh, good question. So we choose the alpha level 0.05, and we're looking for 5% of the least likely events, right? So we expect that the score will fall within these 2 points 95% of the time. If our t-value is less than negative 2.021 or greater than 2.021, you reject the null hypothesis. So our degrees of freedom is 40. Our alpha level for a two-tailed test is 0.05. So you can see that does match up. It's 2.021 for our critical region. So how did we arrive at this degrees of freedom of 40? Well, let's look. First, you obtain the sample data and compute the t-statistic. For degrees of freedom, it's for the first group, it's n-1. They had 25, so that ends up being 24 for the first group. For the second group, it was n-1 for a group of 20 people, which ends up being 19 people. Then you calculate sum of squares for each of the groups, and it ends up being 5,400 for group 1 and 11,875 for group 2. And then we calculate, since we've calculated sum of squares and degrees of freedom for both of our groups, we can now do pooled variance. So we add those two values for sum of squares, and we add the two values for degrees of freedom, and then divide. And we end up with 401.74. All right, so I have that repeated up here. Almost lost track. All right, so for our pooled variance, it was 401.74. And so remember, here is our that pooled variance right there. And so we had scores or mean scores for group 1 of 70. So the mean for group 1 was 70. The mean for group 2 was 74. And now we calculate for our t-statistic, right? We take that pooled variance of 401.74 and divide by the n for each group, okay? Once you do that, you add both of those values, and then you would arrive at 36.16, and then you need to find the square root. Take the square root of 36.16, divide it into 4, which is the difference between our groups' means, and you'll find that the answer is negative 0.67. All right, so t equals negative 0.67. So now we can make a decision. Remember, we had looked up what our t-value was, and so if our t-value is less than or greater than plus or minus 2.021, we can reject the null hypothesis. T was negative 0.67, so we cannot reject the null hypothesis. And if you have to, you can, let's see if I can do the board here, 2.021. Let's see. My goodness. I'm looking for, maybe if I can draw. So even if you have to sort of visualize that for yourself, go ahead and draw a distribution. And you can sort of pretend that you have your mean here. That would be 0. And you have a negative 2.021. So you can imagine that falls somewhere over here. All right, so we have negative 2.02. Sorry, it's hard to draw with this. 1. And then over here, you would have the positive side of 2.021. Now I can visually see. Sometimes people have a little, dyslexia when they're trying to figure this out. So it might be good to have a scratch pad with you if you're doing your homework or your quizzes and tests. So now I can kind of determine, where does negative 0.67 fall? All right, well, it falls between the mean of 0 and this negative 2.021. So probably right about here somewhere, and that's nowhere near the critical region outside of this negative 2.021. So that's why we do not reject the null hypothesis. And then, of course, you need to report the results in APA format. So you tell us, was there a significant difference between the two groups? And it might sound like, and then report the statistics. And in fact, you say there is no significant difference between the tests performances of Class A and Class B. T equals negative 0.67, and the p-value was greater than 0.05. It was not less than 0.05. It wasn't in this 5% that occupies the two tails. So remember, these critical values fall within that alpha level, right, of 0.05 that's split between the two tails. It's a two-sided test that we're calculating for here. Oh, how do I undo annotation? Oh, I see. I don't do this very often, so let's see if we can clean this mess up. Uh, there we go. Okay, I think we got it. And there we go. All right, so here's our first learning check. Which combination of factors is most likely to produce a significant value for an independent measures t-test? So think about what we learned from this last chapter. Logically, you should assume that it should be very similar to the same rules. So let's take a look at what the answer to this first one is. All right, so it would be D, a large mean difference between your groups. That makes sense. And then also small sample variances. All right, is it true that if both samples have n equals 10, the independent measures t statistic will have a degrees of freedom that equals 19? Also, is it true that for an independent measures t statistic, the estimated standard error measures how much difference is reasonable to expect between the sample means if there is no treatment effect? All right, so the first one is false and the second one is true. The reason for the first one being false is you are doing degrees of freedom for two groups now. So if each one of them had 10, it would be like saying 10 minus 2. Or you could say n minus 1 from the first group, n minus 1 from the second group, which would be 18. And also, it's true. This is an accurate interpretation that an independent measures t statistic, that for that t statistic, the estimated standard error measures how much difference is reasonable to expect between the sample means if there is no treatment effect. All right. All right. All right, review. Oh, okay, so typically when I do this in class and we come back, this test is kind of a little different, from the previous tests that we've learned about. And so I kind of go over what we just learned. So we don't really need to do that since this is all in one video. Usually my classes are spread out 2 days between the chapter or for one chapter. So we don't need to review. Although you could use the PowerPoint for study purposes, you can use the review in that. All right, so there's some assumptions that's related to the independent measures T formula. And one is that the observations within each sample are independent. The two populations from which the samples are selected are normal. And the two populations must have equal variances. And we call this homogeneity of variance. All right, so the variance in one group is similar to the variance in other group. All right, so we also should test for this when we're doing our t-tests with two groups. We need to see if the variance is significantly different. So we compute the sample variance for each of the separate samples, which you've already done. Select the largest and the smallest of these sample variances and compute. And you would put the largest on top and the smallest on the bottom for this formula. And then we calculate for the F max. And so the F max value is computed and compared to the critical value found in the Hatley's F max table. And so you can find that Hatley's F max table in your module for chapter 10. Let me go down there. You'll see it right here. Click on that and you can find it. And you can use this for the tests. All right, so here, if the sample value is larger than the value found on the table, you can conclude that the variances are different. And your homogeneity assumption has been violated. If this, in this case here, we do not want to see a significant test. So like when we are testing for differences between groups, we want to see that there is a significant difference. Here, we don't want a significant difference because that would mean the variances between your groups is significantly different. So large values indicate large differences between your sample variances, which is no bueno, no good. Small value, those that are near 1, indicate similar sample variances. And then if that's the case, the homogeneity assumption is reasonable. It has not been violated. However, if you end up having a violation of homogeneity, we can calculate we can adjust the degrees of freedom and calculate. So you can calculate standard error as we did before, but then adjust degrees of freedom for the t-test as given below. So you would calculate as such, as you see here, for degrees of freedom. So once you've changed degrees of freedom, using this formula, you can do the t-test for your two groups. So there's a little forgiveness there. Also, if the null hypothesis is rejected after doing your t-test, the effect size should be determined, just like all the other tests, by using either Cohen's d or the percentage of variance explained. And we looked at this percentage of variance explained in the last t-test. It's the same formula here. You use the t-statistic to calculate for that. And then here, though, we use the estimated standard deviation with pooled variance. And then we subtract for both of the means for both of the groups to calculate for Cohen's d. Also, we can calculate confidence intervals for the independent samples t-test as well, just like and remember, confidence intervals is another way of evaluating effect size. Here, the sample mean difference is used between your two samples is used to estimate the population mean difference. And remember, the T equation is solved for the unknown parameters for the population. So it sort of zeroes itself out. So the estimation can provide an indication of the size and significance of the treatment effect. However, you should note that if the confidence interval contains 0, then it's not a significant effect. So if 0 is within those two parameters, you have no significant difference. If the interval does not contain 0, the treatment effect was significant in this test. All right, so we're going to give you a little example of how to calculate confidence interval if you decided on a confidence interval of 95%. So based on a research study comparing puzzle solving scores for students who were tested in a dimly lit room and scores for students tested in a well-lit room, pardon me. So we have the means for each of those groups, 8 and 12. And we calculated sum of squares of 60 and 66. And we had in each group, we had 8 people, which means if you add them together, -2, right? And -1 for each group, you end up with the degrees of freedom of 14. And then you do your pooled variance here. Remember, you use this formula for that. And then the t-values, we would find that the t-values are located between 2.145 based on our degrees of freedom and our alpha level of 0.05, right? Because we're using a confidence interval of 95%. All right, so we plug into the confidence interval formula, all right, and here it is. So we take the means from each group, 12 and 8, and we subtract, and then we subtract and add that t-value, 2.145, and then we multiply by that pooled variance, and it came out to be 1.5 in this case. Moving to the next step, that subtracted value between the means is 4. And after multiplying 2.145 and 1.5, we find it's 3.21. And we add the 4 to that value and we subtract the 4 from that value. And we end up with a confidence interval of 0.782 to 7.218. So we also remember that the population means for both groups was 0. So we exclude that from the confidence interval formula because a 0 difference is not an acceptable value. So HO would be rejected in a hypothesis test with 0.05 because the interval does not contain a 0. So the treatment effect in this example was significant. Pretty cool. All right, so reporting the results of an independent measures t-test. We would report, remember, we need to, once we've done an experiment and find our results, we have to report our results in APA format. And we can do it using reporting for effect size if we calculated for Cohen's d, or if we used confidence intervals, and you would write that differently for each one. So first you tell, well, here's an example for Cohen's d. You state that the students who were tested in a dimly lit room reported higher performance scores than students who were tested in the well-lit room. And you can see they provide the means and standard deviations for each of these groups. And then they report the t-statistic along with, well, first they state whether it was significant. The mean difference was significant. And then they report the t-statistic, including the degrees of freedom for both groups. So if I look at this 14, and I know it's an independent samples t-test, I know that it's whatever that number was, it was -2. So if I add 2 to 14, I know the total number of participants was 16. All right, and then you report the p-value. In this case, it was less than 0.05, and then the Cohen's d, which is indicated with this italicized d. All right, and then we report with confidence intervals, and everything is pretty much the same, but instead of the Cohen's d at the end here, we report confidence intervals like so. All right, this is a typo. Just one period will do. All right. Okay. All right, so reminder, standard error is directly related to sample variance. So if we have larger variance, this leads to a larger error, which it also leads to a smaller value of t, which means it's closer to 0. And so having a larger variance will result in a less likelihood of finding a significant result. However, if you have larger samples, it can produce smaller error and lead to a larger value for your t statistic. Pardon me. No barking, dog. My dog is barking. No barking. No barking. All right. Hopefully he'll quiet down. All right, so that means you would be more likely to find a significant result. That's enough. He hears another dog barking in the neighborhood. Okay. All right. Here we have an example of what more variance looks like if you're comparing groups, okay? So here's two sample distributions representing two different treatments in the left side here, and they show a significant difference between the treatments, right? Each one had a sample size of 9, and they also have standard deviation is 1.22. This treatment 1 had a mean of 8 and treatment 2 had a mean of 13. And both measures of effect size indicate a large treatment effect. And you can see how both of these groups, the standard deviation is fairly small, right? And you can even see that visually. All of the scores for the groups are kind of clumped together for each group. However, here's kind of what happens or what it would look like visually if you have a much higher amount of variance in your groups. You can see how the scores are overlapping. And look at the standard deviation for their treatments are 6.65 in this case compared to the other one that was 1.22. And when you see that visually, now you can kind of see how it can be very difficult to tell, even visually, the difference between the two groups. Even though these two samples have the same means as the other samples, right? All right. All right, so let's do our final learning checks. For the last one here, for an independent measures research study, the value of Cohen's d, or r squared, helps to describe what? All right, let's see if you can get that one right. It is C. How much difference there is between the two treatments. The key words here is how much, right? Not that just that there is a difference between the two measures or the two treatments, but how much difference there is. All right, that's the key when you're talking about effect size. And the last one, is it true that homogeneity assumption requires the two sample variances to be equal? Also, is it true that if a researcher reports that T with the degrees of freedom of 6 equals 1.98 and a p-value greater than 0.05, then HO is rejected? And let's see what that one is. They were both false. The assumption for the first one requires equal population variances, but the test is valid if sample variances are similar. Also for that second one, HO is rejected when P is less than 0.05 and the T statistic is greater than the critical value of T. All right, well, that covers chapter 10. I'll see you pretty soon for chapter 11.